Hello students, this is Brock Skaggs. I'm going to make this video where we will use SolidWorks Simulation to analyze the planar truss that you see on the screen now. And so a fairly simple truss here. I think we've got 1, 2, 3, 4, 5, 6, 7 different members there. A fixed pin connection on the left hand side at point A, a roller at point C. As far as the cross section goes, we're going to assume this truss is being made out of 1.25-inch Schedule 40 steel pipe, material ASTM A36 structural steel. You can see the geometry before us as far as the dimensions to get the lengths of individual members, and we've got a single load, a force at joint B in the downward direction with a magnitude of 400 pounds. And so some likely questions that you might see are things like what is the internal force carried by each of the truss members, what is the normal stress experienced by each of the members, or you could even ask about the displacements of specific joints as far as at point B, how far down does point B go when this 400-pound load is applied to it. And so we'll see about using SolidWorks Simulation in order to answer some of these questions. So let's go ahead and get into SolidWorks. And so the first thing we're going to do is going to use weldments in order to draw the truss geometry. And so basically, if you haven't used weldments before, what we're going to do is basically make this sketch with just using the lines inside of the sketch environment here. And so what we'll do is I'll get on the front plane. Oop, a little bit of lag there. And so now I've made it to the front plane, and so here I'm just going to very quickly make a rough sketch of this model. It's like I've got a little baby line there that I accidentally generated. And so without any dimensions, there is the rough sketch. The bottom portion have 5 feet long members. And so this will be 60 inches here, 60 inches here. The height of the truss you can see is 2 feet, so this is 24 inches here. And 2.5 there, between this point here. So 2.5 feet, that is 30 inches, and 30 inches here as well. And so very quickly we've made a sketch of basically the center lines of each of these members, which is exactly what we need to start with a weldment style geometry. And so there is the sketch. We're in sketch 1. If you don't have it visible, you'll want to have the weldments tab visible. And so if that's not visible, you just right click on any tab that you do see and make sure that weldments is visible. So for instance here I don't need sheet metal, so I'll turn that off. I also don't need surfaces, so I can go ahead and turn that off. Here if weldments wasn't showing, it might look something like this. And so here I'll have to right click on the tab and bring weldments back there. And so with weldments, what I'll do is go straight into structural member. And remember, we had 1.25-inch Schedule 40 steel pipe. And so here you basically walk down through the drop-down boxes, picking your standard, picking your type, and then picking your size. When you first get into SolidWorks, you have a very limited selection here. Actually, 1.25 Schedule 40 steel pipe is not in the default weldment profiles that you're given. And so you might have to create your own weldment profile depending on your situation there. And so that'll be covered in a different video. Here I've already went through the time to actually create the profile. And so here I can now apply it to the line geometry using groups. And so there's 2 different types of groups, I believe. There's contiguous groups and parallel groups. Contiguous groups are basically groups that form a path where every member connects to another member. And so, for instance, this path around the perimeter of that kind of trapezoidal shape there is one contiguous group. In order to apply these ones, notice I can't click on them now, so I'd have to create a new group, create a second contiguous group in between here. And so that allows me to create the individual members themselves. Here I'm just going to leave all of the defaults here because it shouldn't affect us too much in our analysis. And so at that point I've got the truss geometry here. And so what has happened is basically we've applied that 1.25-inch Schedule 40 steel pipe profile, or that cross section, to each of these individual members. And so that's basically it for the CAD modeling side of this problem. We've got our geometry defined, and we also defined the cross sections associated with the overall truss geometry. Things to check on when you create weldments, you have a cut list, and so the cut list is the number of different bodies we have in the weldment. So just making a sanity check here, you've got 1, 2, 3, 4, 5, 6, and 7, so that makes sense. So the next thing we're going to do is we're actually going to transition to SolidWorks Simulation. And so I've already got simulation added in here, because you can see from the tab here. If you don't have the simulation tab, you'll have to go into the add-ins. So you can click the little arrow down next to the options and go to add-ins. Also accessible through tools and the drop down for add-ins here. And one thing you want to make sure is that you have this guy right here, SolidWorks Simulation, added in. And so you can either add it in to the active session of SolidWorks right here, or you can add it in upon startup every time. Depending on how much you use SolidWorks Simulation, you might as well click the startup one on the right hand side, or if you don't use it very often, you're just going to use it for this specific instance, you would just click the one on the left hand side. Either way will load it into your current session of SolidWorks. And so with that, I'm going to go ahead and make a save here, and so I'll just call this SolidWorks Planar Truss, just in case something does go bad. And so I've got it ready to go at this point. Under simulation, most of the stuff's grayed out at this point. I'm not going to click the study advisor. I'm going to click the down arrow and go to new study. And what I'll do is I'll just leave the default name of static 1, and I'm also leaving the default type. I just want to run a simple static analysis here. And so accepting that now brings me into the simulation side of SolidWorks. And so notice now I'm on a different tab. If you look in the bottom left, I'm on the static 1 tab. And if I ever need to get back to the model side of SolidWorks, I just click the model tab here. And so now I've got two different areas of SolidWorks that I'm working in. Also, you can see with simulation, you've got a different tab and a few new buttons to hit on the ribbon interface, and we've got this kind of split tree environment here, where the bottom side of the tree here is associated with just the simulation side of SolidWorks. And so, what's next? Well, one thing we need to do is tell SolidWorks what material these things are made out of. Are they made out of rubber? Are they made out of steel? Are they made out of aluminum? So on and so forth. And so what I can do is, for this icon right here, navigate down through the cut list so I can actually see all the different bodies. And so here are all the different bodies here. That kind of I-beam shape actually shows that they are beam elements. And so what I'm going to do is just hold control down, and I'm going to select all of the bodies. And so if I pull out, you can see them a little bit better. And I'll right click and I can go apply/edit material. Here I didn't have to hold control. I could have clicked on the top node and said apply material to all bodies. Either way would have got me there. That brings up the usual material library inside of SolidWorks. Here we said we wanted it to be ASTM A36 steel, so I'll just select that. I'll hit apply and close. And what you'll see happen is that now it's reflecting the material next to each one of the bodies there at each node, which is exactly what we want. One other thing we're going to do is help SolidWorks out a little bit by simplifying the model that it's trying to solve, and we're going to make sure that this runs as truss elements. And so in SolidWorks Simulation, you might know that there's different types of elements, and there's solid elements, there's truss elements, there's beam elements, there's shell elements, and so forth. And so here the most appropriate type would be a truss element. It makes sense that we're going to be analyzing a truss system. And so I'm just going to select all the different bodies again. Just by holding control down, I'll right click and I'm going to go to edit definition here. And so under edit definition, it shows that the default setting is beam, and that's because we came from a weldment environment that defaults to the beam types. And so we're going to go from beam and we're going to change it to truss here. And so that's going to be a slight modification just because we're wanting that SolidWorks solver to solve this using truss elements. And so I'll accept that by hitting the green check mark there. One thing you'll note is that the icon changes a little bit here. Notice now we've got this different icon that doesn't look quite like the I-beam that it did before. And that's just showing that, yes, this body is going to be a truss element. And so with the truss element as well as the material, we should be good with this part of the simulation tree. If we walk down through the tree, the next we have is joint group. And so we shouldn't have to do anything, but it's a good habit to get into checking this. Here we'll edit, and we're basically going to make sure that SolidWorks has picked up all the joints we feel are necessary. And so under the results here you can see There's 5 different joints. If you toggle through them and highlight it, you can see the kind of orange icon there, so it's looking at that being joint 1. Here I just want to confirm that there are the correct number of joints. And so in this truss, I've got 1, 2, 3, 4, 5 joints, and it's reflecting 5 here as well. And so this looks good, and we can move on with setting up the simulation. Other times you might have to get in here and play with these values here as far as treat as joint for clearance less than and put some value in here in order to make sure you've got the appropriate number of joints. And so I'll just hit OK. We don't really need any connections for this case, but we do need fixtures. Fixtures are basically talking about how is this model held in space. Right now it's just kind of floating in space, but what is actually going to hold it in place in reality here. And so if we go back to our image here, well, we've got this fixed connection on, or fixed pin connection, I should say, on the left-hand side at point A, and the roller at point C. So those are 2 major fixtures we have to apply to this model. And so what we'll do is I'll right-click on fixtures, and I'll just go to the only option it has really is fixed geometry at this point. But here I don't want fixed geometry. I'm going to use reference geometry for all of these. And so reference geometry is pretty broad. You can see I can select a specific joint here. I can define a reference plane. In this case is what I'll do for this icon. And then I will have the ability to control specific degrees of freedom. And so a 3-dimensional object here in 3D space has a total of 6 degrees of freedom, right? 3 row translation, 3 rotation. And so that's what we're talking about here with these inputs. And so what I'll do is I'll select this joint here. That's the joint that's going to be associated with the fixed pin connection. And then for my reference plane, I usually like to select the plane that the truss is going to be lying in, which is the front plane in this case. That's all dependent on how I drew my initial sketch there to create the truss geometry. So for translations, I'll go ahead and change it to inch since we are dealing with an English problem here, even though it's not going to matter a whole lot. And so first thing I think about is this joint here. That is a fixed pin connection. So in terms of translation, it's not going to be able to translate at all, right? This thing's not going to be able to slide in the X, Y, or Z direction. So what I'm going to do is go ahead and toggle on all 3 of these boxes here. And it's basically going to say, hey, I'm not going to allow the joint to translate along plane direction 1, along plane direction 2, and normal to the plane. And so that's why the 0 is there. So one thing it might be helpful to do is relate these along plane direction 1, along plane direction 2, and normal to plane to the X, Y, and Z directions using the coordinate system here in the bottom left. And so it's all dependent on what you selected here for your reference. But in this case, if my reference is the front plane, along plane direction 1 is actually running this way, kind of left and right. And so that's going to be in the X direction. Along plane direction 2, which is up and down, and that's inside the plane, so that's going to be the Y direction. And normal to plane, well, normal to the front plane is the Z direction there. And so it's good to keep in mind what directions you're looking at instead of just thinking of the very general along plane direction 1, along plane direction 2, and so forth there. So that takes care of the translations. Next for the rotations, right now they're all grayed out, so it could rotate about either any of the X, Y, or Z axes there. And so if we go back to the image, we think about these joints, and they're basically pin connections, and really they're only supposed to be rotating about a pin that's aligned normal to the viewing screen here. And so that would be basically saying that we're wanting to allow rotation about the Z axis for our specific case, but we don't want it to rotate about the X or the Y axes. And so that's exactly what we need to tell SolidWorks here. And so what we're going to do is toggle on the top 2 under rotation. This is, remember, along plane direction 1, which is the X direction for us. Along plane direction 2 is the Y direction for us. And then we're going to leave grayed out the normal to plane one because we do want it to be able to rotate about that Z direction. And so with this combination of inputs for the translation and rotations, we have successfully created a fixed pin connection now for this particular joint, which is joint A, I believe, in our diagram. And so 1 down, a couple more to go. And so now we'll look at C. And so C is going to be very similar. So we'll go back to fixtures, right click, go to fixed geometry, go to use reference geometry. And so then for joints, well, that's the joint here on the bottom right. That'll be our roller. For the reference plane, I'm still going to select the front plane of the assembly. Excuse me, not of the assembly, but of the part. And so now we ask the same questions. Point C, it's on a roller. Can it slide at all? The answer should be yes. It can slide in one direction. That direction being the kind of left and right direction here, which in SolidWorks would be the X direction, which with our front plane, that'll be along plane direction 1. And so we do want it to be able to slide back and forth along plane direction 1, so we'll leave that grayed out. We don't want it to come off the surface, and so what this would mean would be if point C moved vertically, which we don't want to allow, so we'll activate the along plane direction 2 and leave it at 0. And we also want this to be a planar problem, and so we won't let it translate normal to the plane at all. And so that's why we're placing the 0 inside of the normal to area there. So that takes care of translations. On rotations, we think about it again. Well, you have this basically pin connection rolling on the rollers, and so the pin connection part of it's going to look exactly the same as the pin connection part of point A, and by pin connection part I really should be saying rotational part here, because again we just want it to rotate about the axis normal to the screen, or normal to the plane that the truss is lying. And so here we will activate the top two and leave them as zeros to make sure that we don't have any rotation about the X or Y axes, and we'll leave on, or excuse me, leave grayed out the normal two-plane version, which is basically going to allow it to rotate about the Z-axis in my case. And so we'll accept that. At this point, I'm going to go ahead and add one more fixture, and it's going to be the same fixture applied to the interior 3 joints here. And so again, we're going to right-click and go to Fixed Geometry. We'll use Reference Geometry here, and here I'm going to select all 3 of these joints, which are kind of floating here in space. Again, Reference Geometry will still be the front plane. And so you think about these 3 joints, joints B, D, and E. Well, inside of the plane, they're going to move a little bit, right? This truss is not going to be rigid. It's going to go through some deformations. And so we want these things to be able to slide around inside the plane just as they would. And that sliding around is going to be controlled by things like the stiffness of the members there, the material we make them out of, the different cross sections and so forth. And so in order to do that, what we'll do is leave grayed out the along plane direction 1 and along plane direction 2 because we want these things to be shifting around in the plane, but we'll activate the normal 2 plane translation and maintain it at 0. And that way these points don't leave the XY plane or the front plane inside of SolidWorks. Now for the rotation, we go back to thinking, well, these are all pin connections, and so they are all going to be the same idea here. And so we don't want it to rotate about the x-axis or the y-axis. We just want them to allow rotation about the axis normal to the plane, or in this case, the z-axis there. And so that should be appropriate for all these joints that are not attached to anything with respect to the fixtures in the diagram. And so we should be good here. So we've gone through, we've told it the element types, we've told it the material. Now it's a time to tell it the loads as well. We've got the fixtures in here. We're working our way right down this list, and the external loads. Toggling back to the diagram, we see that there's a single concentrated force attached at joint B in a downward direction of 400 pounds. And so going back into SolidWorks, we right-click on the external loads. We've got forces, torques, gravity. Here we're just going to apply a force. Here we've got a lot of different options. Do we want to apply it at a point or a vertex, a joint, or on a beam itself? Well, we want to apply it at a joint, and that joint is this joint right here. Again, it requires you to select a reference plane. That's all. Click the front plane. We'll go to English units, so IPS units, and here we have arrows again to indicate the force that's going to be pointing in the X, Y, or Z directions, as well as a moment that could be causing rotation about the X, Y, or Z directions. In our particular case, we want this guy right here, and we'll reverse the direction. If you can see there, I'll just hover over a beam area. You can see the flippering there. There we go. All those force vectors are pushing downward in the negative Y direction, which is exactly what we want, and it's attached to joint B there. If you have trouble visualizing these, one thing you can do is just toggle them on and off, and you can see the directions here. And so the top one here is going in the X direction, but we don't want that. Again, we want the Y direction going downward, and so this is appropriate. And 400 pounds is the magnitude of that force. So just accept that. So at this point, we're about done with inputting all the information into SolidWorks. One thing we need to do is tell it to mesh, and so we'll hit Create Mesh here. And so since this is a very simple model, it happens almost instantaneously there. Basically meshing, it's basically breaking down this solid model into a bunch of different elements that it does the calculations about. And so here, we're just going to have 7 elements. You can look at the mesh details here and see a total number of elements is 7, just because the truss elements, basically every one of these members is a single element. And so then I'll just come up here to run this study. And so again, very simple models. They run very, very quickly. As you get to more complex models, it might take a much longer time period before it converges to a solution. And so things we were interested in, one thing we'd be interested in is the stresses in each of these members. And so it's showing an upper bound axial and bending stress. One thing, since I know that these are all going to be direct stress cases, direct axial loading here, so these members should be in pure tension and compression. I can come down here, I'll right click on the stress block, I'll go edit definition here. Got some options. I can change the units to PSI. I'll change it to axial. Here it looks very deformed, right? If you look in the top, it's got a deformation scale of over 2,000. So if I want to show, I can say go to true scale. Also under chart options here, I can change it from scientific to floating. I'll just put no decimal places and hit the green check mark there. And so this gets us another view of the stresses on this truss here. And so I've got a few of these values already written down to confirm that we've got the correct solution. So one thing I'm going to do is I'm just going to right click on the plot itself, and I can go to probe. And I'll go normal 2 here on the view. And so one thing probe allows you to do is pick different points of your model, and what I can do is show the values of the different elements. And so in this case, I've got something like this, and I'll just compare to my notes. Roughly 375 in tension for this bottom member here, which is good. This one here, I've got negative 480 roughly, so that should be good. Here, positive 480 is fine, and then negative 750, yes, is fine here as well. So those values look good, and this thing should be symmetric, pretty close. You can see the values on the right and left are quite close to each other there. And so that looks good. For the probes, other things we talked about were the displacements. And so if one was so interested, you could look at the displacement plot. Here it's in the deformed shape, and you can see the max displacement is occurring right there where the force is being applied. It's roughly 0.1278 millimeters there as the maximum displacement. Again, don't be alarmed by the large deformation scale, because you can always come back in here and edit the definition and show at true scale to see what it would actually look like there. So that's a simple truss analysis inside of SolidWorks. We ran a planar truss at this point. We're able to find things out such as the normal stress experienced by each member, and we also quickly looked at the displacement plot there. And so thank you for watching the video, and I hope this has helped you use SolidWorks to solve some of your truss related problems.